let's start. So that's the last class for this course. And so today I wanted to talk more about path integrals and a different approach to path integrals. But I'll start with a kind of digression on Gaussian integrals. So let me recall the setup. First, in the finite dimensional case. So we looked at various Gaussian integrals. So let me recall one of the formulas that we had. So we take v equal to Rn, and we consider the self-adjoint operator on v. And we assume that all the eigenvalues are positive. So we have our n eigenvalues which are all separated from 0. So then we have the following formula for the Gaussian integral, and let me do the following. Let me add a linear term with an imaginary exponential. So the answer will be something like this. 2 pi to the power n over 2 over the square root of the determinant of A, and here it will be minus 1/2 y A inverse y. So that's the formula that we already seen several times. Now let's do the following. Let's define a new measure on V. So now we are integrating with respect to the Lebesgue measure dnx. So let's define a new measure which will be proportional to the Lebesgue measure with the combination of factors from the left-hand side and from the right-hand side. So let's do it like this. So we are taking the factor from the right-hand side. We are taking this Gaussian factor in. And we're taking in the Lebesgue measure. So this is a Gaussian measure on Rn. And of course, now this formula obviously looks as follows. So the integral of the exponential function is equal to this exponential function of a quadratic form. So there is a following fact. Let's call this formula star. In fact, this formula characterizes the measure mu A. And now that in some way That's a promising formula. Because, before, when dealing with those Gaussian integrals in infinite dimensions, right, we spent quite a lot of effort on making sense of the determinant, for instance, already with that. Now in this formula, you don't have no longer any determinants, right? You only have exponentials, which is not a bad thing. So now let's continue our digression, and now let's do the infinite dimensional case. So I now assume that A is an operator with a basis of eigenvectors in an infinite dimensional space. I still assume that all the eigenvalues are positive and possibly growing, or maybe not growing that much. At the moment, doesn't matter. And so we now consider V to be the space of infinite sequences in R. We can also call it R infinity if you want. And we're going to define the following measure. It's an infinite product of measures on each copy of R, where each of these measures, it will be the Gaussian measure exactly of the type that we described here. So, morally speaking, the measure that we are defining here is such a measure, but for an infinite dimensional space. Now, several facts about this measure mu A. So let's denote by pi n the map of an infinite sequence to its first n terms. And let me denote by mu A n the product measure on Rn, right? So the product of those Gaussian measures on Rn. Now just imagine what this mu A is doing. Suppose we have E a product of subsets of R. So this is sitting in Rn. So then mu A of the preimage of E, so this is a kind of cylinder, right? It extends indefinitely in all the other directions, but the first n directions where it is equal to this product, E1 to En, and this will be simply equal to this product. Or maybe, basically, I'm always saying here the same thing. Suppose I consider a function on v with values, say, in our positive, which is defined in the following way. This is some function of n variables computed on the first n components. So then one can compute this integral, and this integral will simply be equal to the integral over Rn, the finite dimensional Gaussian measure times the function of the n variables. Maybe the last thing to recall, A is a probability measure, that is the total mass is simply equal to 1. So this is a kind of formal step, but there is an interesting property of this measure μA that I would like to show you. And this will be motivating for what happens with path integrals. Maybe just the last fact. So suppose that y is a sequence with finite support. So it's equal to 0 after some capital N. So then there is a formula similar to the one that we had before. So this exponential is a well-defined function, right? And the integral is simply the exponential of the quadratic form, as before. So this now the infinite dimensional formula is exactly the same as a finite dimensional formula. We see no problems with any determinants. A minus 1 is very well defined. So y is a finite sequence, so the quadratic form, there are no convergence issues. So this is a very, very tame infinite dimensional story. But actually, it's not as tame as it looks. So let's do the following. Let me denote by A some infinite sequence in V. And let me denote by VA the following subspace. So this will be elements of V such that the infinite sum AI square xi square converges. So this is a kind of Hilbert space type condition. So here is an interesting proposition. Let me try to write down the conditions correctly. So we can actually compute the measures of those subspaces. And it turns out that the result is either 0 or 1, depending on the properties of the sequence. And it is 0 if the sum of squares divided by eigenvalues diverges, and it is 1, if it converges. I don't know whether you find it surprising. I find it somewhat surprising and interesting. So, so in some way, it measures the size of the subspace, and there are only two possible outcomes. It can be either measure 0 or the full measure. Recall that the full measure is 1. That's a probability measure. So this VA is either basically almost everything, or it's nothing at all. So that's one of the rare things today that I'm actually trying to prove. And the idea is as follows. Let's define a characteristic function of the subspace VA as a limit epsilon to 0, limit n to 0, exponential of minus epsilon square, and here's some partial sum from 1 to n ai square xi square. So how does it behave? Suppose that we have an element of V. Then by definition the sum is convergent. So when we take a limit n to 0, n to infinity, when we take a limit n to infinity, so it converges to some finite number, we get exponential minus epsilon square times that finite number. Now we take a limit epsilon to 0. Well, this exponential tends to 1. And of course, if this thing is divergent, we take a limit n to infinity. So this exponential converges to 0, independently of for all positive epsilons. And then we take a limit epsilon to 0, it remains 0. So, so this is the characteristic function of the space VA. So what we need to do, we need to compute the integral over V of the characteristic function, right? That's the measure of the set VA. So this is right. So this is equal to the integral V d mu A of x, and now the limit epsilon to 0, limit n to infinity, and this exponential. Okay. Now, two small remarks, right? About those two limits. Obviously, there is a convergence pointwise, right? So for each x, each of these two limits converges, sometimes easily, sometimes in a more complicated way. Now, it's obvious that this function is always small or equal to 1. And 1 is an integrable function with respect to that measure, right? So this means that we can apply the dominated convergence theorem. So we have this sequence of functions. We can do it both for n and for epsilon. So we always have an upper bound, which is integrable. We have a pointwise convergence. So by dominated convergence, we can actually exchange the limits. So we take out the limits, and we have now here d mu a of x, and here we have exponential minus epsilon square Okay, but these are the integrals that we know how to compute. First of all, these are the two limits. And we can replace the infinite dimensional Gaussian measure by the finite dimensional one. And if I'm not mistaken, the result of the computation is this. So we have a product. So you know this exponential will be adding to the Gaussian exponential. It will change the determinant. We compensated the lambda I determinant, but I think it will be something like this. So the product of ratios of lambda I and lambda I plus epsilon square a square, and then to the power minus 1/2. The limits, yeah, right. Okay. Now, here is a standard fact. If you take now the infinite product, it converges if and only if the corresponding infinite series converges. Right? So now assuming that it converges, right? So it gives some expression which depends on epsilon. And if we send epsilon to 0, it will give us 1, right? Now, of course, if the infinite product diverges, then we get, for any positive epsilon, we get 0. And the limit when epsilon goes to 0 is 0. So that's how those conditions come about, right? And the convergence of the infinite product is exactly the same as convergence of that infinite series. So maybe one remark. So morally speaking, right? D mu A of x is something like this. How was it? We were saying right? So this expression is not right. So if we were copying the formula from the finite dimensional case, we would have written something like this, right? So that should be a kind of formula for that infinite dimensional Gaussian measure. So in particular, one of the well-defined, or maybe the only well-defined thing on the right-hand side is this quadratic form. And this quadratic form, what is it? So this is this series. Now it is well defined. If this series is convergent, right? So this defines for us, so well defined. It defines for us the space that we can call probably V square root of lambda, right? So I mean here that AI is equal to the square root of lambda I, right? So this quadratic form is well defined on the subspace, which is defined by the condition of the type that we are considering, and AIs should be square roots of lambda I. Now, let's see what happens with those sums, right? So if we substitute instead of AI the square root of lambda I, then this is the sum of ones, which is clearly infinite. And so this means that we are falling into this case, right? And this case, this corresponds to the measure equal to 0. So you see that's a kind of interesting thing. Of course, nothing really happens because the formula doesn't make sense anyway. However, in some way, it's natural to expect that the place where we're Gaussian integrating with the Gaussian measure defined by the operator A is the place where the quadratic form of the operator A is defined, right? So that was our intuitive expectation. Now, this simple calculation shows that this is actually completely wrong. So the place where the quadratic form is well defined is of measure 0 under the measure that we kind of defined inspired by this formula. The whole integration is going on some sequences which are growing much faster. Right? So the whole integration happens where this expression is actually infinite. It is a bit strange, right? Because when this expression is infinite, this wants to be 0. But of course, all the other things, they're so infinite, so to say, right? So somehow the compensation happens and there the integration is happening outside that region. Well, all right, so this was a kind of introduction where we can see how things are happening. Now I will define a somewhat more complicated Gaussian measure. And I'm not quite sure, maybe in the other courses you've already seen it. So how much did you talk? Probably you did talk about the Brownian motion quite a lot, or did you not? So you know what's the measure or what the Wiener measure or not really. Okay, so I'll briefly recall you the Wiener measure, and that's what we're gonna use. And that's a measure of the same type. Okay, so here is a theorem. Maybe I state it in a somewhat strange way, but maybe you will tell me whether you recognize it. I will formulate it in Rn. So for each x in, oh, do I want it in Rn? Maybe, yeah, let me do it in R as we were doing all the time. Okay, for each point in R, and each pair of positive real numbers, sigma and t, there is a unique measure mu x sigma. So it will be a measure on continuous functions on the segment 0t. And this small x, I will choose it to be the value at the end point. I think usually the Brownian motion people would define fixing the value at the starting point. But for us, it doesn't matter basically. For us, it will be somewhat more convenient to fix the value at the end point where the Brownian path comes. And now, here is the condition. So such that for all here I'm always getting confused. You see, kind of, it's strange. I have to order it in the other way. So T naught is the biggest one and Tn is the smallest one. So I consider some partition of my interval. And for every measurable function, let's take it positive again. We have the following formula that I will probably write here. So integral over the space and now I'll put a function f of x right? So I'm taking, again, a function of some finite number of values. Those values, they will be the values of my path at the points t1 through tn, right? So I can imagine the following picture. So this is t. So this is my point x. So that's this Brownian path, and here there are the points. In particular, the Tn is the starting point, right? And I don't know where it is, right? I know where the last point is. So this is equal to the following interesting expression. So this is a product from 1 to n. Here 1 over square root of 2 pi sigma. Now tj minus tj, no, tj minus 1, right? Minus tj. Because j is a decreasing sequence. And here an integral over Rn dx1 dxn. And here I'm writing the following Gaussian measure. 1 to n, and here x. Right. So does it match your expectations for the Wiener measure? Not so much that you have from the other courses. So you see it's defined in a similar way as we did before, right? We define a measure on some, this time rather horrible, infinite dimensional space. So that's a space of continuous functions on the segment which with the endpoint fixed. And we define it by that property that we have those finite dimensional properties. We can take our path, we can look what it is at some finite number of points, and for that finite number of points, here is the finite dimensional Gaussian measure, and for this finite dimensional Gaussian measure, we say that the integral should match. So, so that's the property which defines it. Now, one remark and one fact. So this sum j from 1 to capital N xj minus 1 minus xj squared over tj minus 1 minus tj. So we can rewrite it as like this. So I divide and multiply by tj minus 1 minus tj. And now this is a Riemann sum for an integral. right, for this Riemann integral. So we just take a derivative of our path squared and we integrate it. Of course, if the derivative exists. Now we say our function is only continuous, maybe it's not differentiable. So this so maybe actually derivative does not exist. Now the fact that I'm not sure, maybe actually you also know from the other courses. So the following fact. Let's define the following subspaces of the space of continuous functions, which are defined by the Hölder condition. So supremum of what do I want? Yeah. Right, so we consider this Hölder type conditions, right? So these are subsets of Cx, and we can ask what's the integral, or what's the measure what's the Wiener measure of those subsets. And the answer is, by now, is not surprising for us, but it's kind of interesting. So it's again 0 or 1, depending on alpha. And it is 1 for alpha smaller than 1/2. And it is 0 if alpha n is between 1/2 and 1. In particular, again, you see, so for this thing to exist, say if we are continuously differentiable, we are of course in the class C1. Now, if we are in the class C1, then the measure of this class is 0. So it's a kind of the same type of phenomenon that we observed with that simpler measure. So it turns out that basically, yes, in some sense, this expression is an approximation of the Riemann integral of x prime squared. But where we actually plan to integrate with that measure, of course, we want to integrate where the measure is non-zero, right? Somewhere. So this integral actually doesn't make any sense. Or maybe that will be good for us for the discussion of the next hour. So those Brownian parts, they are much rougher than the differentiable parts. But I'm not sure, probably in the other course you covered it, or you kind of about Brownian motion, you kind of know things, right? All right, so let's have a break, and let's continue after the break. All right, so let's continue. The last calculation in the course goes under the name of the Feynman-Katz formula. So let's go back to the basics. We are looking at the Schrödinger equation. the time-dependent one. And usually we were choosing the Hamiltonian to be minus the second derivative with a coefficient plus sufficiently nice potential. And now the idea is as follows. So let's replace t with minus it. So this is a kind of strange move, but let's see what comes out. So the equation changes, but it still has roughly the same form, right? So you get some other equation. It's also a first order in t, an equation with an operator h. Well, and let's furthermore assume that v of x is bounded from below. So we can also rewrite the right-hand side as minus h naught plus v, and h naught is the Hamiltonian of a free particle, right? Well, so we can get interested in the following question: how to build an evolution for this new operator. So the evolution u of t is now exponential of minus 1 over h times capital H times t. Of course, we can also consider such a thing. Why not? And let me rewrite it one more time. Now both operators h naught and v are self-adjoint and bounded from below. And under favorable circumstances, we can use the Lee-Trotter formula. For the Lee-Trotter formula, we should probably add a vector, right? And here this will be limit n to infinity, exponential minus 1 over h naught t over n, exponential minus 1 over h v t over n to the power n times psi. Well, now that's basically the calculation that we were doing when constructing Feynman path integrals. Now we'll need the propagator for the free particle. So exponential minus 1 over h naught t psi naught. And for psi naught nice enough, this is given by the following formula, which is basically very similar to the formula that we had before. And this is computed at x. So in fact, the equation now with H naught without V, that's the heat equation. And that's the propagator for the heat equation. Right? And the heat equation in our case is so that would be the heat equation. As you see now, instead of oscillating, the exponential is falling very fast when x is different from y. So in some way, that's a much nicer kernel. And simply following the scheme that we had with the Feynman path integral, we can write it down. Now, what will it be? This will be mn over 2 pi h bar t to the power n over 2. And here an integral, sorry, always a limit, of course. An integral dx1 dxn. And now, well, okay, so this will be the exponential. So in the exponential, I think I should copy this, right, divided by t over n, and here the sum j from 1 to n, xj minus 1 minus xj squared. Is it all I should write? Maybe you should probably control what I'm doing, right? And here will be minus 1 over h sum j from 1 to n v of xj, right? And here will be a psi 0 of xn. How am I doing? Is it correct? Hopefully, probably. So this comes from those kernels, and as before, times t over n, right? Times t over n. And here that's the right one. Does it look good for you? So here I'm replacing t by t over n. And these are simply the kernels of multiplication operators by exponential of minus 1 over h v of x times t over n. So otherwise the calculation is more or less verbatim the same as the one for the Feynman path integrals. There they were imaginary exponentials, here they're real exponentials. Okay. Now I would like to rewrite it as a limit n to infinity. And instead of now I would like to replace this integration measure with the integration measure for the with the integration measure that we introduced with the Wiener measure, right? So this will be d mu x equal to x0, right? And now we should probably choose sigma. So sigma will be h over m.
And in this integral, this is a function of what, which variable?
This is a function of x. Equal to x0. And here, right, here x0 enters, enters when j is equal to 1. So it enters this exponential. Yeah, so this is a function of x0. Right. So I would like to rewrite it as an integral over d mu x 0 h over m. And now, like, that's my splitting, right? I'm simply splitting with the distance t over n. And here will be the exponential minus 1 over h sum j from 1 to n v of xj times t over n psi naught of xn. Right. So here I'm just using the definition or whatever, the defining property of the Wiener measure, right? So this is just an identity. Now, one remark. Suppose I have a path, and suppose that psi naught is a square integrable function. And I would like to consider psi naught of x of 0. So then, by definition, an integral over cx of psi naught of x of 0, right? It's equal to this factor, 1 over square root of 2 pi sigma t, and then an integral, let's say dy, right? So that's simply the definition how Wiener measure integrates. Now, this is clearly in L2. So this means actually for psi naught in L2, this integral is well defined. So this implies that actually psi naught of x of 0 is in L1 on that space. Right. So maybe that's the first remark. Another remark. Let's say v of x is a continuous function. So then v of xs is also a continuous function. And this means that the Riemann sums converge to the integral. So here, right, I don't need to differentiate anything, right? Recall last hour we had a discussion that this integral of x prime squared, if it is defined, right, then the Riemann sums converge to it, but maybe it's not defined, and usually it's not defined. But this guy is always defined for continuous functions, so this is just the Riemann integral. And one more remark. Assume that psi naught is nice. So being nice, let's say, it needs to have values, right? L2 functions, they don't quite have values at points, but let's assume that psi naught is a nice function. So then exponential minus 1 over h sum from 1 to n b of xj t over n psi naught of xn converges when n goes to infinity to exponential 1 over h integral v of x of s ds psi x of 0. So this simply converges pointwise, meaning for every pass. And the absolute value of this thing is bounded by exponential minus 1 over h c times t times psi naught of x of 0, where c is a lower bound on the potential. Right? And this is an integrable. So this estimate is an integrable function. So again, kind of you see, I'm trying to bring it to the dominated convergence. So actually this expression for different n, it converges pointwise for every pass, and also it's dominated by some function which is integrable with respect to the Wiener measure. So this means that by the dominated convergence I can again exchange the limits. And this is equal to the integral g mu x naught h over m, and here exponential minus 1 over h So this is the Feynman-Katz formula. So you see we obtained the evolution, well, not for the Schrödinger equation, but for the equation closely related to Schrödinger. We change time to imaginary time, and after that, this is a real integral of an infinite dimensional space of continuous functions. So that's what we should integrate. So it turns out, right, before in the Feynman path integral, we had a classical action, and the classical action has this kinetic term with a derivative and the potential term. Now the kinetic term, in some way, it is there in the Wiener measure. So the potential, that's what remains. It turns out that on continuous passes, the potential is still nice enough, so this term makes sense, right? So this integral does make sense, and it gives us a well-defined expression. It's a bit difficult to say. It is a highlight of this path integral story, because this is the real path integral, which is defined mathematically. Of course, then still we need to do something with our time, which now is kind of imaginary time. So the usual law is how you do it. Then you obtain some answers which depend on time, and you're supposed to analytically continue back to hopefully obtain solutions of the Schrödinger equation. So then there would be also a question of how to analytically continue it. But we're not going to discuss it today. Instead, I thought maybe we still continue. So that was the last result I wanted to show you. I wanted to continue for some minutes and tell you a little bit about the perspective of this story in quantum field theory. So these are remarks or comments. So maybe I'll give you 3 remarks. So the first remark. Typically, in quantum field theory, we would like to replace the action functional, right? So up to now, we were looking at action functionals of this type. We want to replace it with something like this. So let me symbolically write down something, and then we'll see. So now this is an integral over the space of dimension n plus 1. So n equals 0 corresponds to classical mechanics that we were looking at. Now we can imagine that this is an n-dimensional space, and there is a time direction, right? So that's our picture. Now phi's are now maps either to R or maybe to some other space of dimension M. And typically you want your action to be quadratic in derivatives, as here. Maybe it has some quadratic term that's similar to the oscillator problem that we were looking at, and maybe it has some potential which in general would be a sum of some kind of homogeneous functions of phi of homogeneity k. So cubic function plus quartic function plus so on. So one would like, in general, one would like to define path integrals of this type. So now what happens, it turns out you can define Gaussian path integrals. So for that, as you know, you need a quadratic form. And as a quadratic form, you simply take the part of your integral which is quadratic in phi. Right? So you take a quadratic form, a bit similar to what we were doing today with a Wiener path integral. You can define Gaussian integrals corresponding to those quadratic forms. So now the question is what you need to define. So suppose we have such a measure of phi. C1 and C2 will be its parameters, similar to sigma, right? See, before we had a parameter sigma, so there will be those parameters. And here we want to define whatever, either with imaginary, but let's say right? So we would like to define something like this. So that was the question before. And you know, before it worked very well. Now the question is where this measure will be supported, right? So before the Wiener measure, a great thing about it, it's supported on continuous functions. Okay, those continuous functions are too rough to have derivatives in general, but they do have values, and therefore you can define v of phi. So the problem is that starting from n equal 1, that is starting from two-dimensional field theory, for n greater or equal than 1, phi is too rough to define v of phi. So that becomes problematic, right? Before we encountered a little bit of that problem because the x prime or x prime square were not defined. So our functions in the support of the measure were too rough. Now they will be too rough even to define v of phi. So that's actually the reason sometimes one says that in quantum field theory you have infinities. So that's one way to see it. So then kind of, you know, if you attempt to define x prime square for x not a differentiable function, you can say, okay, your derivatives, they will be infinite, right? So here this guy will now be infinite and you need to do something with it. So that's how you get those infinities and then eventually renormalization, how you try to get rid of those infinities. So that's roughly how you get into those problems of quantum field theory. Okay, so in some way one can say that there are many things done about it, but probably still there is no ultimate theory of path integrals. So, and that's as in many things with integration theory. You know, there is not, as you know from your calculus classes or analysis classes, there is not one integration theory, there are many. So here as well, there are some integration theories, but maybe we still haven't found the correct one. Like, right, when Lebesgue came up with his integration theory, that was a big change with respect to the Riemann integration theory. So similar here, maybe we don't integrate in the right way. So one more remark. It's difficult to avoid mentioning it in quantum theory class. So that's the Clay, Millennium, Young-Mills problem. Actually, one of the problems of defining path integrals in higher dimensions is considered as one of the biggest open mass problems. And so there the theory is as follows. So we take n equals 3, meaning the realistic three-dimensional space-time in which we live. So n plus 1 is equals 3 plus 1. Now we should choose the concrete form of those of the fields. So here actually it's going to be as follows. So the fields are like that. And let me choose the simplest case, A equal to 1, 2, 3. So in total there are, how many? 4 times 3, 12 fields. And so out of these fields, we build the following combination. Let me try to write it more or less correctly. Where epsilon ABC is a completely skew-symmetric tensor. So if this is a positive permutation of 1 to 3, it's plus 1, and if it's negative, it's minus 1, and it's 0 if it has repeating indices. And then S of A is equal to 1 over some constant integral of right. So that's the action functional in that problem. As you see, right, so this expression has a linear part and a quadratic part. This means that this expression, which will have a quadratic part, plus a cubic part, plus the fourth degree part. So, of course, so this Clay problem, I looked it up how it's stated. I think the description is roughly 14 pages. So I will not repeat it now, but maybe 2 elements of it. So what do they want? So one thing they want makes sense. Of the path integral like that. So that may be one way to state the question, but there is a somewhat sharper way to formulate it. Right? Before diving into path integrals, we were looking at spectra of self-adjoint operators. So another way to say it, maybe for this problem you want to define a spectral problem. A spectral problem. So find the Hilbert space H. and a self-adjoint Hamiltonian H. And the problem prescribes some properties of this H. So we want this H to be bounded from below, and that's what usually people in physics want. And prove that the spectrum of H is of the following form. So it's bounded from below. So it starts somewhere. So it has a point, so the leftmost point is an eigenvalue. And then there is possibly a continuous spectrum to the right, but there is a gap. In that spectrum. So that's what is, at least that's what is expected. So the conjecture is that if you properly define the Hamiltonian for this problem, then it will be self-adjoint on some Hilbert space. It will have a ground state which is an eigenvalue, and then there will be a gap. There will be nothing till the next point of the spectrum, which is probably a point of continuous spectrum. So it sounds very concrete. It sounds very much in the framework of our course. So you can take it as a homework, right? Now, maybe the last remark. So a non-trivial example for n equal 1. That is the 1 plus 1 dimensional fields theory. With v of phi, the exponential function. So actually, in the Taylor series, you have contributions of all degrees. Will be one of the mini courses at the winter school, or actually even two, but one of them will be a probabilistic approach, a little bit similar, but of course a lot more advanced, as we outlined today. And then the other one will be a very algebraic approach, or differential equations approach. So actually two mini courses at the winter school will be about some example of a two-dimensional quantum field theory and how to make sense of it, and how to make sense of its path integral. All right, I think that's it for today, and actually that's it for this course. Thanks a lot. That was really nice to work with you. I hope you didn't suffer too much in my hands.